All right, good morning. So today is already the 10th lecture for the course. We'll start talking about a new topic today, which is uncertainty. And more generally, what we'll see is connected to deep generative models, so neural networks that you can use to generate data. So today we'll see a few things around that topic, but we'll mainly focus on what we call neural density estimators, so generative models that you can use to generate data, but also to evaluate the density value of any data point. Okay? And so this is the first lecture of a sequence of 3 lectures on that topic. So today we'll talk about basically types of uncertainty, how to estimate densities with neural networks. We also talk about Bayesian deep learning. Then next week, or not next week, but after the Easter break, we'll talk about variational autoencoders, which is a class of generative models that you can use to generate any kind of data. And finally, we'll extend that to diffusion models, which is another class of generative models that you can use also to generate data. Okay, so usually these lectures they are a bit more difficult for the students because the mathematical background is maybe a bit easier than for the others. So if what I'm saying does not make any sense to you, just feel free to interrupt, and I will try to explain as much as I can. But so don't be shy and ask questions, please. All right. So I will start maybe today with this quote from Carl Sagan, who was a physicist. And this is a quote about uncertainty and uncertainty in the context of science. And he says the following: every time a scientific paper presents a bit of data, so basically a result, it should come or it comes with an error bar. Okay? And this error bar is really, really important in my opinion. And he says that this error bar is a quiet but insistent reminder that no knowledge is complete or perfect. Okay? It's only a calibration of how much we trust what we think we know. Okay? So basically, every time you present a result, or every time you see a result, this result only makes sense if you can associate to it some notion of uncertainty, how much you can trust or how much you trust this result yourself. Okay? And so this is what we'll try to do today. We'll try to design neural networks that not only, for example, can make predictions, but can also associate a level of uncertainty with these predictions. Okay? Because think about what would happen if you have to deploy a deep learning, a deep neural network to solve some task. Eventually, certainly, you will use these predictions to make a decision. But if you can't trust the predictions, then certainly the optimal decision should make should change. Okay, if you get some predictions, but the certainty is very high, then certainly you can be confident yourself and use these predictions to make a decision. However, if you can assess that the neural network itself is not very confident about its own prediction, then maybe your own decision that you will have will be quite different. I will come with a few examples. But more practically, if you look at this quote, basically every time you read a scientific paper, or even if you look back at some of your own reports, every time you present a piece of results, if this result they don't come with error bars, basically they are quite useless from a scientific point of view. Because you can't know if you can trust or not these results. Okay, so the menu for today will be as follows. We'll try to answer this question: how to estimate uncertainty with neural networks, but also of neural networks. I will start with maybe describing what I mean by uncertainty. We'll see various kinds of uncertainties. And then we'll focus today on 2 types of uncertainties. The first one is what we call aleatoric uncertainty, and the second one is epistemic uncertainty. Okay, so uncertainty. Can you tell me what that means to you? How would you define the concept of uncertainty? What does that mean? You're not sure. Yeah. Oh, yes. So it's when you don't know, and no, but it's exactly that. It's when you don't know, and what could be the reasons you don't know? The noise. The noise of what? Of sensors. Yeah. So you could have. You could be in a setting where you are measuring things, you are collecting data, and the instrument that you use is imperfect, is noisy, so it introduces random variations to the measurements, basically what we call noise. Could there be other settings where you are uncertain? Yeah. Like what? Can you elaborate? Like, can you tell me what's behind the door? You can guess. Okay, is there an elephant behind the door? It's very unlikely. Okay, you don't know for sure, but you and so you don't know exactly, but you can still associate a level of confidence with that. Okay. So formally, I would say that uncertainty refers to situation settings where there is imperfect or unknown information, and that can arise for several reasons. So it can arise in predictions of future events. So of course, we don't know the futures. We can make guesses, but we'll be uncertain about these guesses. It could happen in physical measurements because of noise in instruments. But also it could happen in situations where the information is unknown, like the last example we talked about. Okay, and accounting for uncertainty is really necessary in the context of decision making. If you don't account for the uncertainty that you have about predictions, that will necessarily lead to suboptimal, wrong, or even catastrophic decisions. Okay, so just to show you, I will pick two examples today to tell you about the importance of uncertainty under decision makings. So this is quite a quite old example already. So this is the first fatality of a self-driving car back in 2016, where the passenger, not the driver in this case, actually died. And it died because the system on board the car was not taking into account the uncertainty about the environment. And in this case, what happened is that, so if you see the scenario there, so the car was driving this way along the road, but in the opposite direction was coming a truck, a white truck, and it decided to turn left to go over this road. And the car basically didn't see the truck because it was white. And the system, the cameras and the self-driving system, in this case, mistook the side of the truck for the sky. And so if there is only sky in front of you, you can just move forward. Okay, so in this case, the prediction that in front of the car there is no obstacle, there is sky was wrong. Okay, it may have been uncertain, that we don't know, but it was wrong, and that led to the accident. Okay, so this is an example where if you base your decisions on wrong predictions, then things can go wrong and very badly. So this is another example where no one died, but what happened is that there is in this case, another self-driving car that comes to someone. You can call your car with your phone. And in this case, it didn't see, again, this obstacle, in this case, just a plane. Because this is not a setting where these cars are really trained to be, like driving on inside an airport with planes on the road. So these are unexpected or very rare events, but this is precisely where accounting for uncertainty could have been quite helpful. Another example, this happened in a system deployed by Google a few years ago, where the goal was simply to annotate images like you have in Google Photos. And in this case, so you have images that are correctly labeled, but you see for these two people, they are incorrectly labeled as gorillas. Okay? So this is quite wrong, okay? Obviously, and that raises many concerns in terms of bias, racial discrimination, and many other important things. But again, it's because the system or the programmer decided to trust the predictions of a neural network in this case, without taking into account the confidence of this neural network. Okay? So the system that made these errors, they were very likely to be confident in their predictions, and they did not account for uncertainty. If instead uncertainty was taken into account, then certainly we would have seen in either of these cases that we were in scenarios, in settings where the uncertainty of the system was quite high. And in this case, certainly maybe we could just have, for example, in the case of the car, decided to stop, or in this case, decided not to label any image. Okay? It does not mean that if you take into account uncertainty, you will be correct. Okay? That's another issue. But at least you can avoid some bad scenarios, because you can be incorrect and confident. Okay, so the first type of uncertainties we'll talk about today is what we call aleatoric uncertainty, which is basically just a fancy word to say that we refer to the uncertainty of the data itself. Okay. So it's the uncertainty that arises from the stochasticity of the true data generating process. So there is really something, a natural process or a physical process that led to the data that we have, and this process is stochastic. Okay? And so this is a type of uncertainty that will not be able to reduce. It's not because you collect more data that the uncertainty of the process will reduce. Okay? So we'll have to cope with this uncertainty no matter what. And a very, very common example of that is simply the noise that you would have from observations, from noisy observations, because of imperfect instruments. So every time you collect data, that will happen. Okay, so we'll talk about two subtypes of aleatoric uncertainty today. The first one is what we call homoscedastic uncertainty. The second one is heteroscedastic uncertainty. Basically, just say whether or not the uncertainty changes as a function of the input. If you assume that the uncertainty is everywhere the same on the input space, then we are in the homoscedastic scenario. On the other hand, if you make the assumption that or if you are rather in a setting where the uncertainty, so the noise, can change depending on the input, then we are in the heteroscedastic uncertainty case. Okay, and so this is what you see for two very simple scenarios in these two plots, where you would have some input through some variable x1, and then you have a second variable x2. Okay, and then you just look, for example, at the variation of x2 given x1. In the homoscedastic scenario, you would have that basically the range of values, or rather the size of the range of values, or the variance of x2 given x1 is the same across the input space, is the same across all values of x1. And on the other hand, in the heteroscedastic scenario, you would have, for example, that the variance of x2 can change depending on the value of x1. So, for example, in this case, to the left, you would have small variance for x2, but as x1 gets larger, you would have larger and larger variance. And you see that the spread of the values of x2 increases. Yes? I'm not talking about errors. It's just noise. Okay, so you collect some data and you formalize that with a variable, a random variable. And I'm just saying the electric uncertainty refers to the variability of that variable. Okay, but that variable does not need to be something about errors. Okay. Okay, so let's say we want to model these uncertainties with a neural network. Okay, so formally, what we'll try to do, or we'll consider a setting where we have some training set as usual in the form of a pair of input and output. We'll assume as usual that these pairs, they are drawn from the joint probability distribution of the inputs and outputs, so P of X and Y. Okay. We'll assume as usual that X is described by a vector of features and that Y is just, in this case, a scalar value. Okay. And when we say we want to do neural density estimation, we are basically saying that we are not really interested in just trying to make a point estimate of Y given X. So we are not interested in just learning a function, a deterministic function of X that would produce some scalar value, scalar estimate for Y. What we are interested instead is to estimate or to learn rather the entire conditional distribution of Y given X. Okay, so that will be the object that we'll try to learn with the neural network today, is this conditional distribution of Y of some output given some input X. Okay. Okay, so we assume a data set of pairs and what we want to learn is P of Y, the conditional distribution of the output given the input. How could we do that? How could we learn this object? Where we are in a setting today where Y is just a scalar value. Yes, yes. Je sais pas si ça aide, mais. So what kind of assumptions could we make, and then how could we learn this object? Yes. Mm-hmm. Okay, so what kind of assumptions could you make in this case, for example? Yes. Okay, so we are making the assumption, okay, that, for example, Y follows a Gaussian distribution, and we have to specify the parameters of this Gaussian. So we need a mean and a covariance matrix. How would you set them? Okay, and what would be the input of this neural network? Yeah. So we could say that we have a neural network, mu, that depends on its own weights, its own parameters theta, that will take X as input, and we could have a second neural network that will produce as output, for example, the variance of y given x. Okay? And here we'll make the assumption that we have a diagonal covariance matrix. Okay? Okay, so if we want to deal with the homoscedastic scenario first, we'll basically say that if we remain under these assumptions of a Gaussian distribution for the output given input, we'll basically restrict, in this case, the variance to something which is common to all x, so therefore does not depend on x. Okay? So we'll just have, in this case, that py given x follows the same Gaussian distribution, but the variance does not depend on x. Okay, and this is what you see in this diagram, where we'll have a neural network that takes as input the data x, the input. The neural network comes with its own parameters, all its weights, everything that we have seen, depending on the architecture of the neural network. Everything is denoted under theta. The output of this neural network is some vector, which we'll call mu, and which we'll use as the mean parameter for the normal distribution that you associate to py given x. Okay? But this normal distribution, it requires two parameters, so a mean vector that we have, but also a variance. So in this case, we just say this variance sigma squared is itself a parameter that we'll have to learn. And now that we have these two parameters, we have fully specified the normal distribution. And the only thing that is left is then to use some value of y for which we want to evaluate the density. Okay, and that produces the density as output. So how can we learn this neural network? Or how can we learn these two parameters, theta and sigma squared? Mm-hmm. And when you say optimize, what do you mean? Okay, so we will just do maximum likelihood estimation. Okay, so let's do that. So we have to solve basically this problem of identifying the best parameters theta star and the best variance sigma square star. And we'll do that by solving this maximization problem of the data given the parameters. Okay, where D, is this. Okay, so we have the likelihood over the entire data set. If we make the assumption that these pairs that are drawn from the joint are drawn identically and independently, we can rewrite this joint distribution over all the pairs as a product over the xi, yi of p of in this case, if we only care about the output, yi, xi, so this is equal then okay, so what is py given x? Py given x is our model. Okay, it's what we have assumed just there, so it's just a Gaussian density. And so we have 1 over square root of 2 pi times the variance that we have to learn, times the exponential of minus the square difference to the mean. So we have yi minus the mean. What is the mean? It's the output of the neural network to the square over 2 sigma squared. Right? Yes. Okay, as usual, I will transform this maximization of the density as the minimization of the negative of the log density. And so the log of a product becomes a sum. And so this one will become a sum minus xi, yi. Then we have this term. So we have the log. The log of this big product becomes this sum of logs of these things, which are themselves products. So we can further rewrite this as the log of 1 over, so that's, so this is a constant. Okay, so we'll have the log of a constant minus this, log of some constant minus log of sigma. Okay, then we'll have the log of the exponential that becomes just this. And we have a plus. Okay. And that can be further rewritten. So I will have this. Off. This does not depend on the parameter, and this one will become a plus logarithm of the variance. Yes. Okay. So this is the regular regression case. So if you say, if we had instead made the assumption that the variance was fixed and not a free parameter that we have to learn, we could have further written this. So this would have disappeared, and this one also, because we don't have to minimize them anymore, and we would have obtained just the regular regression objective, which is the one of minimizing the sum of squared errors. Okay? But now we are taking into account uncertainty, so we are fitting the variance, and we'll have this. How do you interpret this expression? So how can we minimize this quantity? Yeah. No, I mean, yes, but okay. So when would it be minimized, rather? Yes. Yeah, so this expression would be, at least this term would be 0 when the numerator is 0. So when the mean is exactly at the values. Okay. How could we also minimize this quantity? Yeah. Yeah, so if you can't make a good prediction, an alternative way, which you see emerging from this expression, is that in this case, just say that you don't know, meaning increase your uncertainty. If you increase the uncertainty, you will basically do that through the variance. You will have a larger values for sigma, and so you are increasing the value of the denominator, which will decrease the value of the ratio. However, of course, you can't just trivially say that you're uncertain and you increase the variance to infinity, because you will be penalized for that. Okay, because the logarithm of plus infinity remains plus infinity. Okay? So it's a trade-off between making correct predictions or assessing your uncertainty about these predictions. So basically saying that you don't know what should be a good value in this case. Okay? Okay, the second scenario is the one of heteroscedastic uncertainty, where now the variance will become a function of the input x. So we are more or less in the same setting as before, but the difference is that instead of having a shared and global parameter sigma square, now sigma square is no longer a parameter, it's an output, it's a quantity that will compute as a function of x, and we'll do that in the same way as for the mean with the neural network. Okay, and so we can do that, for example, by having a neural network that produces two quantities as output, the mean vector and the variance, or the variance sigma square as output. Again, we can follow exactly the same recipe to train this neural network. So we'll do maximum likelihood estimation. Given the data set, we'll maximize the joint density of the pairs, given the parameters theta of the neural network. That can be written again as a product of the conditionals of the output given the input. Then we just use the modeling assumption. In this case, we assume a Gaussian. But now the difference, you see, is that sigma is now a function of x. Okay, so you have sigma x there and also there at the denominator. But then we can do the same trick, minimizing the negative of the log density to arrive to this final expression, where now we get exactly the same, except that, again, the variance is a function of x. So now that means you can, the model can have the freedom to either make very confident predictions by adjusting the variance for some inputs, or in some other region of the input space, the network can also say, I don't know, and would be doing that by just increasing the variance instead of making or trying to make correct predictions. Okay, trick question. Let's say you have x, the input, just as a vector of p element or d element, I don't know. What was the... And then you design some neural network, like an MLP. And you want this MLP to produce mu x or let's say this is just a scalar value for mu, so mu, and a variance. So can you tell me how I should implement that, or rather how I should implement this last part, the output of the neural network? How can I make the network to produce several outputs? Yes? Okay, so let's say that the layer just before produce some vector that we'll call HL. Okay, what you are saying is that now you will say that you will have some output with two elements, sorry, and you say that this is the result of some matrix times HL product, where you have dimension, for example, W, such that it produces two outputs. Okay, so you would basically have a last linear layer that goes from this quantity to two quantities. All right? Yes? Why would you do a softmax? Yeah. Yeah, but we need to predict the parameters of this distribution. No. So if you would insert a softmax there, and then what? Yeah, but so the softmax will produce values between 0 and 1. You take the mean, you will have some value between 0 and 1. But y can have a mean value which is outside of 0 and 1. Yeah. Okay, well, let's say you go for this. You insert a linear layer with two output elements, and you say the first one is the mean, and the second one is the variance. Then you implement this. You start training. What you will see is that you get a lot of non-values. What do you do to debug this? Yeah. What do you normalize? And what do you mean by normalizing the last layer? Use batch normalization, layer normalization, or something else? Yeah. No, they are proper. Everything is properly set. So you have initialized the weights properly, and so on and so forth. So when you evaluate the loss, you get nuns. Yeah. Okay, so you'd say your solution would be to say sigma square. So let's call this z. So we have, in this case, z0 and z1. And you say you define the sigma square as z1 plus epsilon. Okay, you will still get that. Yeah. Yeah. So you think the problem is because sigma square can be equal to 0? Yeah, that could happen, but it's very unlikely that from the start the neural network will produce, since it's randomly initialized, a value there at this second element which is exactly 0. Yeah. What do you mean when you square? So this output is what you interpret as the variance. Okay, you don't take the square of that. Mm-hmm. So the issue is rather this term. Yeah. Sure, correct. Where have we said that this quantity must remain positive? Nowhere. Okay, so unless we do something to fix that, that quantity can be negative. It's very likely that for some inputs it will be negative. Then and if we say we interpret this quantity as a variance, we take the square root to obtain the standard deviation of a negative value. That's already difficult. But if we manage that, we even say, okay, we'll put that into the log. And anyway, so that's not defined. Okay, and that's why you get non-values. How do we fix that? Yeah. Taking the absolute value. Yeah, could work. The issue is with the absolute value is that we still have this unlikely, but that could happen scenario where the output is exactly equal to 0. The absolute value will be equal to 0, we'll be dividing by 0. Yeah. That's already a better solution, but now you will restrict the value of the variance to something between 0 and 1. And you could have values, you could have variances that are much larger than 1. Yeah. Yeah, but you will get... then now you will... when you take the value of this, for all the z1 values that are negative, the value will be 0, and you will be dividing by 0. Yeah. Yeah, you just exponentiate this quantity, and now you interpret the exponential the exponential of this quantity as the variance. Okay, or rather, you could say that z1 is the log of the variance. Okay, and now the log can take any value which on the real line. Okay. You have questions so far? Okay, so this is nice, but we have made a very big and certainly wrong assumption, which is to say that py given x follows a Gaussian distribution. It's very likely that this distribution will always be adequate to model the actual distribution of the output given the input. So for example, if we have a multimodal distribution, so if the true distribution is something like this, so we are at some x, okay, and we look at py given x. Okay, if the true distribution is maybe something like this, and we say, oh, but that thing I will approximate by a Gaussian will be fitting something like this. Okay, so that will be in yellow, that will be our model. And of course, this model will be quite bad because it will produce values that are very actually unlikely, or it will poorly explain the actual data. So how can we fix that? How can we increase the capacity, basically, of our model? Yeah. Yes, and what would you do with these Gaussians? Let's say you have 3 of them. So, sorry, you? Yeah. So you can just consider a weighted mean of Gaussian distributions. That's what we call a Gaussian mixture model, where now we'll say, instead of just saying we model the output density by just a single Gaussian, we'll say that it can be multimodal, and we'll do that with this parametric model in which we'll have a sum of Gaussian densities, each with their own mean and variance parameters. And we can also have the freedom to set the weights that we associate to each component of the mixture. Okay? And why do we need these weights? Because it could be, for example, that we are in a setting like this, where it's maybe something like this. Okay, so you would have the bulk of the density there, and you could have a first component modeling this part, and then you could have a second, but for which the weight should be much lower. Okay, and if you say you just sum these Gaussians, you will not be able to model this scenario. Okay, you need the weights. Okay, so now we are considering a more complicated models with more parameters. Where the parameters are the mu k, the sigma square k, and the pi k, the weights. We need a constraint on the weights for this sum to be a proper density. The weights should be each positive, and they should all sum to 0. Okay? Yeah. No, just a Gaussian mixture model. Sure, but yeah, you could say that this is a special case of an ensemble models where your model are Gaussians, if you want, but yeah. Okay, and then in terms of architecture, this is now the network that we would obtain, where we have a neural network as before with its own parameters, taking the input x as input. And then the neural network has to produce now many more parameters, not just a mean or a variance, but all the parameters that you need to instantiate each component inside the mixture, and also the weights that you associate to each of the components. So we have mu k, sigma square k, and pi k, which we repeat k times. Okay, so that means the neural network has a number of outputs which is equal to k times 3 if we are dealing with one-dimensional scalar output values. And then we have the same thing as before. Each component, you can use it to instantiate a Gaussian distribution, then from which you can obtain the density of some output, y, and then you sum all these densities, but you weight them by the pi coefficients, and that gives you the final density that you associate to y. Yes? Yes. Yeah. It's something which is fixed, which you don't learn, but of course, which you should tune, like the number of layers or the size of the layers. They are fixed, but you should tune them. It's exactly the same. Okay, so as an example before the break, let's say we consider this data generating process where we have some input x, and we'll say that the output value is generated according to this expression. So the output is equal to x itself plus 0.3 the sinus of 4 pi x plus some random noise epsilon, which is drawn from a Gaussian distribution. Okay? So if we generate data, input-output pairs, this is the kind of points we would see. Okay? And let me just switch to... Okay. And so if we start with the data in blue and we fit a regular MLP where we would minimize simply the squared error, we would have the fit that you see in red. Okay, so it's not too bad. And it's actually fitting to the conditional mean of the output given the input. Okay, you see that the red one is more or less centered on the range of values of the blue points, and that's the case more or less everywhere. Okay? Now, what if we switch the inputs and the outputs? So the outputs become the inputs and the inputs become the outputs. Now, this is the kind of plots we would have for the pairs in blue. But now if we switch and try to train the same MLP, which can only produce one single output, this is the kind of results we would obtain. How do you explain that? Yeah. Mm-hmm. Yeah, exactly. So we are on this part of the plot. So since the network is only allowed to produce one output, and we are minimizing the squared error, the quantity that we'll actually be trying to estimate is just the mean of the output given some input, so at some position. And we are in this scenario where we have something which is multimodal, and we try to fit this parameter, the mean. So we will manage to do that, but that mean will be just in between the two modes and will not be very useful. Okay, so that's another reason why dealing with uncertainty or distributions for the output is already interesting. If we just make point estimates, and we obtain them by minimizing the squared error, every time we have something multimodal, nothing will work really well. Okay, what if instead we train a mixture density network? So a mixture of Gaussian distributions where parameters are each predicted by an MLP. So in red, you see realizations out of this Gaussian mixture model, random realizations as we train. And now you see that the neural network managed to put densities everywhere you have data. So, for example, if we take the same region there, you have density in this region for Y, but also in this region and in this region. Okay, and the network is able to do that because it can divide the density through the various components it can play with. So it could say there is a component there is a component there, and there is another component there. Okay? Yeah. So I don't know exactly what is used for this particular demo, but you need for this problem you need at least 3 Gaussians, because you have at most 3 modes. Questions? Yeah. Yes, yes. Just so the Gaussians, they are nice because they are usually easy to optimize. If you try to fit a uniform distribution, you will be trying to fit the bounds of these distributions, and the data that you will have will be either inside or outside the distribution. And so it will be constant. It's either this or that. Meaning the gradients, if you make small changes to something, I mean, certainly they will be equal to 0 too. Yeah. What do you mean? Oh, it will work too. So actually, this GMM is quite powerful, and you can show mathematically that the more components you put, the better. And they are universal in the sense that if you put sufficiently many components, you will be able to approximate any distribution. But for this to happen, you may need a quite large number of components. Yes?
How do we know at least how many we should use? Because here we already know what the data should look like, but when we don't know.
You don't know. Yeah. Yeah, you don't know. That's an hyperparameter. So it's like asking, how do I know the architecture of the neural network I should use? It's the same question. Okay? But you are correct in saying that this is an hyperparameter that maybe we don't want to have to tune. And it would be nice if we could have neural networks that are more powerful and can directly adapt to, depending on the complexity, I would say, of the output distribution given the input. And this is what we'll see just after the break with normalizing flows. Okay? So let's take a break. Let's resume at 9:45, 10 minutes more or less. Okay, we'll continue. Okay, so we have talked about already 3 kinds of neural density estimators. So remember, what we want to do today is to solve this problem of having a neural network which would be by itself estimating or modeling this conditional probability of some output y given some input vector x. So we have seen, okay, we can just assume we are in the scalar case and we'll say that y follows a Gaussian distribution, in which case the neural network should produce the parameters of this Gaussian distribution, so the mean and the variance. This can be done in 2 ways. Either we have a global variance parameter, okay, but in this case we would be lacking in flexibility, or we say that in the heteroscedastic case that the variance is dependent on the input x, in which case we make now this variance also an output of the neural network, which we use as an input parameter of the normal distribution. And what we have just seen before is that, okay, this, regardless of having the variance a function of the input, this model has very limited capacity because it's unimodal. It assumes a Gaussian distribution. So as soon as these assumptions will not all, this model will be bad. And so a better model that we could assume, or at least a model with more capacity, is a Gaussian mixture model, which is basically saying that instead of having one Gaussian, we'll assume that we have several of them, and we just take a weighted mean of their densities, and we say that this mixture is our conditional distribution of the output given the input. And that works to some extent, but this model is also quite limited by the number of components k which you pick. And usually, what will happen is that if you have really a complicated distribution to model, you will require many components K for this to be a good model. Okay. So now we'll see a quite different architecture, which we call a normalizing flow. The goal of this normalizing flow is still the same. It will be to estimate this conditional density of the output, but will not do that by saying that the output is a Gaussian or a mixture of Gaussian. Okay. The trick that we'll use is what we call the change of variable of random variables. So let's consider this diagram where we have some random variable z, which let's say is uniformly distributed in this square or in this cube. Okay? And then we say, okay, what if we consider a change of variable? What if we define a new variable x as a function of z? Okay? And one simple scenario would be when we define x as twice the value of z. Okay? In this case, now the range of values of x becomes everything inside this cube. So if along this dimension z could have taken any value between 0 and 1, let's say, now along the same dimension, x can take any value between 0 and twice the upper bound of z. So in this case, 2. 2 times 1. And the same for the other dimensions. But what about the density that we associate now to this random variable x? And what if we know the initial density of z, and we know the change of variable, so we know the mapping, the function f, mapping from z to x. Okay? So in this case, we can re-express the probability density of x. We have made the assumption that x is something that we can compute from z. So x is f of z for some z. Okay? But if we know z, and if we know the base density of z, then we can rewrite this density as the density of z, which has been used to generate x, okay, times the ratio of the two volumes, times the ratio of the volume of z over the volume of x. And in this case, we would have pz times 1 over 8. Okay? And we have if we have a multidimensional if we have multidimensional variables, so for example, if really they are three-dimensional, then this 1 over 8 in this case actually corresponds to the inverse of the absolute value of the determinant of this matrix, which represents, in this case, the Jacobian of the linear transformation x. Okay, so where does that come from? Okay, so the thing that we need is what we call the change of variable theorem. So let's assume that we have a base distribution for which we know the density over z, over some variable z. And we know pz. And let's say, for example, that we have something like this. Okay? Then we define a new variable, x, and we'll say that x is equal to some function f of z. For example, 2z in the case of the slide. Now the question or the thing we want to estimate or that we would like to have access to is the density of x. So what will happen? So if So let's say 0 is there. Okay. If we say, just for the sake of the example, that x is twice z, if we are there, okay, we'll multiply this value by a factor of 2, and we'll arrive there. Okay? And we'll arrive there, and so on and so on. Okay? And if we are in the negative part, we'll arrive there, more or less. Okay? So, and the resulting distribution now would be something which is flatter, because we have stretched the space z to go from when we go from z to x. No, it should be even flatter than that. Okay, sorry. Okay, so this is px. Now, can we derive mathematically an expression for px? Well, if we take, for example, this part, and we approximate this region by a rectangle, so this rectangle contains some density of pz. Okay, and it contains a density equal simply to the area of this rectangle. Right? So let's call this delta z, and this one corresponds to pz. Okay, the value that we can read there at pz. Okay, so these rectangles, we can use them to approximate the entire density. Okay, and so on. Now, when we make the change of variable, what we'll do is that we'll transform also, so these elements inside the rectangle, inside the base of the rectangle, will be stretched. Okay? So if we look at this one, so this segment here now will be maybe something a bit larger, twice larger as before. Okay? But the density that is inside this rectangle should be preserved. Okay, so if the range here is twice larger, the density, if it's preserved, should be something like this, such that the area between this rectangle and this one remains the same. Okay? And so you can do that for all rectangles that you stretch by 2, at least for the base, and so on and so forth. So if the density is preserved, that means the area of the white and the yellow rectangle are the same. Okay? And why do we need to preserve the density? Because if we stretch by 2 and we impose this to be a density, it should integrate to 1. Okay, that's why it should be preserved. So we have, so let's call this delta x and this one px. We have that px times delta x, which is the area in yellow, is equal to the area there in white, which is pz times delta z. Okay, so from this equation, I can rewrite it in 2 ways. I can say that, so I can isolate px and rewrite it as pz over the ratio of delta z and delta x. But x is nothing else than the output of f evaluated at z. So this is the same as p of f z, equals to pz. And I'm just here renaming x with delta f. And this is itself equal to pz. And I will just do a trick there. I will take the inverse like this. Okay? Now, what if delta z goes to 0? In this case, what we'll have is that P of f c equal pz over the rate of change of the function, or rather the instantaneous rate of change of the function. So the rate of change of the function when the change in the input becomes infinitely small. Does that remind you of any quantity? It's the derivative. Okay, so, but if you are in the multidimensional case, this becomes the Jacobian matrix. Okay, and so this term is a matrix. Okay, so it's the matrix of the partial derivatives of the outputs given each input. Okay, and this is when you take the absolute value. Is no, there is a. Yeah, so the absolute value is equal to, in this case, the determinant, or is it missing? Let me check. Yes, it's missing. Okay, it should be the determinant here. Okay, and we can do the same in the other direction. So when we rewrite this as px equal pz times, okay, if f is something that we can reverse, okay, we can, so if we assume that z, so from x we can go back to z, we can re-expect the z's as functions of f through the reverse function. So f minus 1 of x of f minus 1 x. Okay, and now we have something similar when delta x goes to 0. We have that p of x is equal to p of minus x times the determinant of Okay, so this says that if we want to evaluate the density for any data point x, and if you have expressed x as a function, as a transformation from z, then how do you compute it? You reverse the mapping, so you go from x to z, you arrive somewhere at z, for which you know you can evaluate the density, but you need also to take into account the change of volume, okay, through this term, which was the same as this one, at least for this expression. Okay? Okay, what if f is nonlinear? What if we assume basically any kind of change of variable? Then we would have something like this. Let's say we start from some base distribution like a Gaussian distribution on z. Then we define a change of variable like this curve that you see in blue. Okay. If you assume, in this case, this change of variable, the resulting density would be the one that you see there in orange. But we have exactly the same logic. If, for example, we are in the shaded region there, in this case, we have that the function increase very quickly. So it's stretching basically the z values. So in this case, this small segment is stretched to this one. But if we want again to maintain or preserve the density, if we want this area to be the same, that can only happen if we also at the same time reduce the density for the corresponding axis. Okay, so before you see the density was high, but now it's lower because we have stretched the range of values. And on the other hand, when the change of variable is a function that changes very slowly, then we are in this case considering, for example, this range, and we are packing all these values so more or less into the same region in the output space in X. So we are basically projecting all the initial density into a small region. And so this is what would happen there. We have put this large part of density into a small region. Okay, so now the base will be smaller, but the density will be higher. Okay? And this change of, this is really what happens. And this is why we have these expressions. Okay, so generally speaking, the change of variable theorem says that if f is nonlinear, then the Jacobian of the function f represents the infinitesimal linear transformation in the neighborhood of z. Okay, and if we further assume that that function f is bijective, so we can go from z to x, but also from x to z, we can go backward. Then the density should be conserved locally. Okay, and because of that, the local change of density, so the preservation of the area of the rectangles, yields these two expressions. One where we express, where we use the forward transformation, and in this case we have this ratio, so the inverse of the determinant of the forward mapping going from z to f. But we can also use the reverse mapping, and in this case we would have to multiply not by the inverse of the determinant of the forward mapping, but by the determinant of the inverse mapping, of the determinant of the Jacobian of the reverse mapping. Okay? Questions? Okay, so this is a nice result because it tells me I can start from a base distribution, like a Gaussian distribution. I can change this distribution through some change of variable f. Okay, and I will still be able to evaluate the density after this change of variable. Okay, and specifically, if I can go back, so if I can go from data x back to z, because I have something that I can inverse, then I can evaluate either of these two expressions. Okay. So now the trick of a normalizing flow, or first of a layer that we find in a normalizing flow, is to say, well, this function f will be a neural network. But a neural network with a very, very special property, a neural network that I can reverse. Such that I can, from the output of the neural network, I can compute its input, and vice versa. If we can design such a layer, then we can apply the change of variable theorem and directly evaluate the density. Okay? And then basically the trick will be to design a neural network with sufficient capacity, such that it will be able to find the right change of variable to properly model the data distribution. Okay, so how can we possibly do that? So there are many kinds of layers that you can find in normalizing flows. I will only explain one of them, one of the simplest. It's also not the most powerful, but it works more or less. So let's assume that we have a z vector, and we want to map this z vector to an x vector. Okay? And we'll divide these two vectors into two parts, two halves, za and zb, which together, if you concatenate them, will produce z. And the same for x, we'll divide x into two halves, xa and xb. So we assume that we have some input vector z, okay, and we'll call this za, and this one zb. We'll define the output also as a vector of the same size, by the way, as the same dimension as z, and we'll call that xa, and this one xp. All right? And now we'll try to define a mapping that goes from z to x, but a mapping such that we can also go backwards. Given x, we can recover z. Okay? So in a coupling layer, what we do is that we say, well, the value of xa will be za itself. Okay? So xa is equal to za. And then we'll say xb will be a function of both za and zb. And what we do is that we compute some quantity that we call s from za. We take the exponential of that. So basically, this is now just a positive quantity, or a vector made of positive elements. And we say that we multiply each element in zb by each element in this vector, computed from za. So this is, you should see that basically as a scaling. We will be rescaling the elements of zb through some function s, okay, which we compute from the first half of the elements. So we'll be rescaling, and we will also be translating the elements through some other quantity, t, which we'll add now to the rescaled value of zb. So we are rescaling and now shifting the values, and we say that this is zb. This is xb, sorry. Okay, so this is what? This is zb, S of the A plus T of the A. Okay. So what are S and T? S and T are neural networks of any kind. Okay, so they could be, for example, MLPs. Okay, how do we go backward? Given X and XA and XB, can I retrieve the A and the B? Okay, so this is the A, the B. Well, if we have said that XA is the A itself, then from XA you can recover the A because this is the A itself. Okay, so this is immediate. The A equals XA. And now that we know the A, we can compute the offset and the scaling factor because they only depend on the A. Okay, and shifting and rescaling is something that we can reverse. We can just shift in the opposite direction of the offset and rescale inversely by S. So from now XA, I can compute the offset T through the same function T, which I can remove now from XB. That will produce this value that we have there. And now we have the exponential of this thing, which we can rewrite in this case as, because we are using the exponential, it's as if we would be multiplying by exponential of minus S. Okay, and okay. Which means that this is equal to XB minus T XA times the exponential of minus S XA. Okay, so this is an example of a layer that we can inverse. Of course, so as usual, we can go from inputs to outputs, but because of the structure of the layer, we can also go back from outputs back to inputs. Okay, so it seems that you are in the setting where we can invoke the change of variable theorem. Okay, so if we say now that X is these two halves of XA and XB produced by this coupling layer, then we can evaluate the log density of X by saying this is equal to the log density of Z times the inverse of the determinant of the forward of the layer. Okay, we are using this expression, this one. Yeah. Which preserve the dimension only that. So you take the neural network S, you produce some output, and then you negate this output. That's it. Okay, so if we have that, then we can so we need now to think about this, the Jacobian of the forward of the coupling layer. And in this case, it's nice because it can be expressed as a block diagonal, where we have, for the first block, the top left block, we have the identity matrix. Why? Because we use just an identity. The first half of the output values is the first half of the input. Okay, so in this case, the Jacobian of this identity mapping is the identity matrix. The input. The other elements, ZB, they are not used to produce ZA. Okay, so in this case we have zeros for the other element. Then for this one, well, we have a dense block in this case, which corresponds to the Jacobian of XB given ZB. Okay. And finally, we have the dependence of XB to ZA there, which in this case simplifies to a diagonal matrix where the diagonal is made of the exponential of the S values. Okay. So if you take this and you differentiate with respect to ZB, okay, this is that block, that last block. So when you differentiate this one cancels. This one is just a coefficient, but which remains after taking the derivative. So you are only left with that. Okay, so that's the Jacobian. And what you should notice is that the Jacobian matrix is a lower triangular matrix, which is super nice because if you have a lower triangular matrix, the computation of the determinant of that matrix is just the product of the elements on the diagonal. Okay, so that means the ratio of the volumes, which we compute by taking the absolute value of the determinant of the Jacobian matrix, reduce to just the product of the elements on the diagonal of that matrix. Okay, and so we are taking the product of the first half of the diagonal, which is made of ones. So that's one. And the second half, which is already a diagonal matrix 2. And so we just have to take the product of this term, so the exponential of the S values. Okay? And since now we are computing a product of exponentials, that can be written as the exponential of the sum of the terms on the diagonal. Okay? Which means now that if we take the logarithm of the density, okay, so we have the logarithm of this product becomes the sum of the logarithm of the base density plus the logarithm of that thing, which we have shown to be equal to the exponential of the sum over the diagonal elements. So with the log of the exponential, that simplifies, and we are left with something really simple, which is just the sum of the diagonal elements. Okay? So that means you can put some capacity in these two neural networks that will define a change of variable which you can reverse. You can invoke the change of variable theorem. And so now you will be able to evaluate the density under this change of variable of your data. Okay? And that's the loss that we use. Okay? We just maximize the likelihood of the data. Except now that we have defined the likelihood through this change of variable and through these invertible layers. Okay, so effectively, we'll just be maximizing this expression. Okay, but you may tell me these coupling layers, okay, I understand that they can do something for the second half, but if you say that the first half is equal to ZA, then this value will not follow any other distribution than the distribution of ZA. Okay? And so that's a very limiting factor. So the trick then is to say, well, I will do deep learning, so I will consider several of these layers. So I will consider now a sequence of coupling layers. And in between two layers, what I can do simply is to swap the two halves. Such that at the second layer, this part which was not changed inside this coupling layer now will be changed in the second layer. Okay? And if you do that, you obtain a normalizing flow, which we define as a composition of layers which are each invertible. Okay? So normalizing flow is now a big change of variable f that transforms a base distribution pz into px through a discrete sequence of invertible transformations. Okay? And so really the picture you should have in mind is that the process that we assume is to start from a base density for which we know the density, like a Gaussian, and then we'll consider a sequence of changes of these variables. So a first one which would go from z to z1, let's say, and then from z1 to z2, and then from z2 to z3. And then we name the last of these variables z, the x variable. Okay? So this would be the forward direction, but if we design at the same time each of these transformations to be invertible, okay, we can go backward. We can go back from x to z, so x which is equal to z3, to z2, to z1, and to z. Okay? And so mathematically, now if we chain all these things together and apply the change of variable, so we have this. This defines the change of the change of variable as a composition of invertible layers from 1 to k. Okay, and the change of variable you can apply it sequentially, and everything now will reduce to this expression. Okay, where we have the logarithm of the base density minus the sum. So we are now just iterating over the transformations. And every time we account for the change of volumes by computing the absolute value of the determinant of the forward transformation. Okay? Does that make sense to everyone? And so this is very, very powerful. With these normalizing flows, provided you put enough capacity and you mix correctly the variables in between two layers, you can very easily model discontinuous distributions. You can also model multimodal distributions. So what you see there are data points drawn from some artificial data distributions. And then you train a normalizing flow on these data points. And then you resample or you evaluate the density, and you get, in this case, very good reconstruction of these distributions. And the same architecture can be used. So in this case, the same architecture was used to model all these 7 distributions. Okay. If you were, for example, to try to fit a Gaussian mixture model on this data, yeah, you would need many, many components. Okay. Here you can just be a bit stupid and say, okay, you consider a very big normalizing flow with many layers. You put enough capacity in S and T, and then that's it. You let the neural network figure everything out. Okay, so how does that relate to our initial problem, which was to estimate the conditional density of something given an input? Well, we can extend normalizing flows, which are made really just to model densities, not conditional densities, by adding context information C. And the trick will be very simple, just to say, now this S and T neural network, they will also take some context C as input. And now, what you would be learning, if you have pairs of C and X, is a normalizing flow which models, in this case, P of X given C. P of some data given some context C. Okay? And if we are interested precisely in this problem of modeling some output Y given X, then that means the context would be X and the data itself would be the Y values. Okay? So we would have a normalizing flow modeling a distribution over Y, but conditionally on X. Okay. This is another example of what you can do. So of course you can do this two-dimensional distribution, but these are just toy distributions. If you want to try to have a distribution over more complicated objects like images, you can start doing that with normalizing flows. And this one is an example of a normalizing flow, a conditional normalizing flow made to increase the resolution of an image. And so the goal is to have a normalizing flow which produces a distribution over high-dimensional images, P of X at high resolution, given as context, given as input, a low-dimensional image. Okay, so here, if you look back at the slides and then zoom in, you will see the pixels, and this is the ground truth that we want to retrieve when we upscale, or when you upsample rather these images. And these are realizations that you can get out of a conditional normalizing flow. Okay. Also, there is no way you would be able to produce images with a Gaussian mixture model, but that's something you can start doing with the normalizing flow. Questions? Okay, last, before the break, instead of considering a discrete sequence of transformations, you can also assume that you have infinitely many transformations. Okay? And so this is what we call a continuous time normalizing flow. And the trick is to say we replace the discrete sequence of transformations with an ordinary differential equation, which is parameterized by a neural network. Okay? So we'll do something similar. We say that we start from some z drawn from some known distribution. And instead of just stating a transformation that would go from z to z1 and then to z2 and z3, okay, we just specify the instantaneous transformation. And we'll do that through an ODE. And so when we have to say that we define the derivative of z at some time step t with respect to t, and we have to specify this function. Okay, so we define the derivative of z with respect to time. Okay, and what we'll say is that this derivative is something that you specify, guess what, as a neural network. Okay, so we'll say f is a neural network that will take as input the current state, the current time step, its parameters, and will define as output the derivative with respect to time. And then we'll say that x is the value of z that we reach when we go continuously from 0 to 1. Okay, so x is z1, which is defined as z0, the starting point of the sequence, the infinite sequence of transformations, okay, which in this case is defined by the integral from 0 to 1 of the derivative with respect to time. Okay? And what is nice is that the change of variable theorem also applies in the continuous case. And we arrive to this expression for the log density of the data. It's still the same expression. The log density of Px, the log density of x is equal to the log density of z0 minus the integral of the trace of this thing, which is the Jacobian which is the Jacobian of the f function with respect to the state zt. Okay, but really, I mean, you should not be scared by this expression. If we look at this one, now we are just doing a sum, not over from 1 to k, but over infinitely many terms from 0 to 1. So this sum becomes an integral. Okay, and this log determinant of the Jacobian of the forward changes becomes the trace of the Jacobian of the f function. Okay? Yeah. No, just solve the integral. So you define the change of variable in a continuous way. And then you say you go from some times, you start at t0 and you stop at t equal 1. Okay, and that's how you define the mapping from z to x. Questions? So I'm having this slide because when we'll have the very last lecture, when we'll be talking about diffusion models, I will also show you that a diffusion model is a special kind, or is more or less equivalent to a continuous summarizing flow. Okay? All right, so let's take a break of 10-15 minutes, and then we resume. Okay, on continue. All right. So we have just seen a new class of neural network to estimate and model densities. So these normalizing flows. So you can use them every time you want to model a distribution. And what is really nice and actually a bit special about this architecture is that you can also evaluate the density of any data point x, which is something that we'll not have access to in the following lectures when we talk about other kinds of deep generative models. Will not have a direct access to the density. So that's something quite unique to normalizing flows, the fact that you can directly evaluate the density of any x, okay? And since you have that, you can just do maximum likelihood estimation, and you are good to go, okay? And so just a quick recap, the trick of a normalizing flow is to define a change of variable, starting from a base distribution z. We define the change of variable, and then we arrive to some other distribution. And the trick will be to align this other distribution to the data distribution. Okay? So I had the question during the break. This z's I'm talking about is not something we have access to in the training set. Okay? We have only access to x's. Okay? But we'll be able to map these x values to some z because we define a change of variable which is invertible. And because of that, we can evaluate density. It should be conserved. That leads to this expression, where we define the density of any x by mapping x to the z connected through the f function, for which we know we can evaluate the density, but then we need to take into account the change of volumes between the two densities, which we can obtain by multiplying by the inverse of the absolute value of the determinant of the Jacobian matrix of the forward transform that goes from z to x. Okay? And I realized there that, so when I did this step, there we arrived to this, of the ratio of delta f over delta z. Okay? And here I added the determinant So in the one-dimensional case, this is not necessary, because if x and z are both one-dimensional vectors, the Jacobian is made of one unique element, which is the derivative of f with respect to z, which is this thing. Okay, and it's only when we have more than one dimensions that then this ratio of dimensions becomes this determinant. Okay. One thing also which is important for you to realize is that when we define the change of variable, we are mapping these of the same dimension as the x's. So if you have vectors of 100 elements for x, you must also define a distribution over these which are also 100 dimensional vectors. Okay, which can be a constraint. Okay, because when z will become something very high dimensional, that means z will also be very high dimensional. Okay. Do you have questions about any of this? Okay. Okay, next and last topic for today, epistemic uncertainty. So epistemic uncertainty is another kind of uncertainty which does not relate to the data generating process, but relates to everything we know we don't know. Okay? It's basically how much we trust the model that we are fitting to the data. Okay? Because so you can be uncertain about this model, because, for example, there could be several models that can fit the data. Which one should we prefer? So this subjective preferences is also something that you can encode through uncertainty. Okay? So epistemic uncertainty will account for the uncertainty in the model itself. Okay, so this is a subjective uncertainty, or in the parameters of this model. Okay? And the goal of this uncertainty is to capture our ignorance. Okay, everything we know we don't know. Okay? And this is a kind of uncertainty which we can reduce by collecting more data. Okay, contrary to aleatoric uncertainty, which we cannot reduce by collecting more data. Okay? So what do I mean exactly? So we have seen so far many architectures of neural networks that you can use to map data. Okay, that would go from inputs to outputs, and they would work more or less well. Okay? But these neural networks, they depend on parameters. And it's easy to realize that there could be actually several configurations of the parameters that could work equally well actually on the data set that we have. So why should we prefer one over the other? So what we'll do now in what you call Bayesian neural networks is to say, well, I will have a prior beliefs about neural networks, which will be expressed as a prior distribution over the weights, over the parameters. Okay, so I start with some prior beliefs, prior uncertainty about what I think should be a good neural network. And then I will do a Bayesian update, given the training set that I have, to obtain a posterior distribution over the parameters given the data. Okay. Okay, so this is what we call Bayesian deep learning. And so we say that we start from a prior, which will be a distribution over weights omega of some neural network. Okay, and a priori we have preferences about what should be a good or a bad neural network. Okay, and we encode these preferences through this probability distribution, which we call the prior distribution over the weights. Okay. Then we have data. So we have a data set D of, for example, input-output pairs, as usual, or something else. Could have also just have axis if you are dealing with neural density estimators, but this would be the classical setup where we have a data set of input-output pairs. Okay. And what we want to do is to say, when we'll have to make a prediction, we'll not just use one neural network, the one that fits the best the data, okay, but instead we'll do a model average. We'll consider all possible neural networks for all possible parametrizations. Okay, so there will be infinitely many of them. And we do a weighted mean of their predictions. And we weight the predictions proportionally either to our prior beliefs that we have about neural networks or our updated beliefs when you do a Bayesian update that goes from the prior to the posterior over the parameters. Okay, so what is P of omega given D? So P omega given D. Well, using the Bayes rule, we can re-express that as the prior that we have about parameters, which we reweight by how good or how well the data D is explained by this specific neural network. So P of D given parameters, and we normalize by the evidence. Okay, so now what I'm saying basically is that instead of just considering one neural network, I consider all possible neural networks for some given architecture. I consider all possible parametrizations of some architecture of neural network. I start with some prior beliefs about these parameters. Then comes a data set. I will use this data set not to produce a best fit, but instead to update my prior beliefs and to obtain a posterior distribution over neural networks. And I will only select those which are likely under my prior and that explain the data well. Okay? And so what's the point of doing that? The point is, I can switch to this one. The point is to rewrite the conditional distribution of the output as the average prediction of all possible neural networks that we have weighted by either the prior or the posterior beliefs that we have about these parameters. So this is what we would call the prior predictive distribution, where we say, okay, I've not observed anything, I have no data set, I just have my prior. In this case, I say that py given x is py given x and given the parameters omega of some neural network, except that we will consider all possible neural networks, and I will average by their prior density. Okay? And now, if data comes, if we have access to a training set D of pairs, we do a Bayesian update to go from these prior beliefs to the posterior distribution of the weights parameters given the data. And now, if we can compute this quantity, we can rewrite our predictive distribution as a posterior predictive distribution in which now we have condition on the data. Okay, and it's the same as above, except that we replace the prior by the posterior. Okay? Yeah, this is what we call the Bayesian model average.
I'm not sure I understood the goal that we're trying to use. Are we trying to identify the best model given the data that we have to approximate the X? Or
Okay, so yeah, that's a good point. Let me motivate what we are doing. Let's say this is X, this is Y, and this is your training set. And you fit a neural network on that. You have 2 points. If you do a best fit, as we've seen for 10 lectures, you will get some neural network like this. Should you trust these predictions? No, in this case, you don't know. So you should take into account the fact that you don't know. And the only thing that you can resort to are your prior beliefs about what could be a good function. Because if you then train another neural network, maybe you would have had something like this. And the predictions you would do anywhere outside of the training data would be quite not random, but arbitrary or heavily dependent on the architecture that you've chosen or on the specific configuration of the parameters that you arrive to. If you are being Bayesian about that, you are just saying, I have prior beliefs about the functions themselves. And instead of saying, I pick one and only one among those, I consider all of them. And when I have data, I will just update my prior beliefs with this data to restrict to only those that are compatible with the data. Okay? So if your prior beliefs would have been, so before seeing any of these 2 points, you can have functions more or less within this range, and so you occupy the whole density there with some functions that are more or less smooth. That depends on what you want. And then you say, okay, now I update with 2 points. You would be effectively updating this distribution, maybe with this, to only those that passes through these 2 points. Maybe there, if you assume, and then maybe there. And now the resulting density, the posterior predictive density, would be only this part inside, and this part there. Okay? Does that make sense? Okay, so, all right. So we have to compute this guy, the posterior distribution of the parameters given D. So that we know, that's our prior distribution of the parameters. We can assume we know and we can evaluate everywhere. Do we know this P of D given omega? What do you mean? We don't know that? Given D, given some data and given omega, can we evaluate this density? Why is it difficult? You mean it's difficult to evaluate, or it's difficult because you don't understand? No, in practice it's super easy. Can we evaluate this term? You say yes, why? And why can we evaluate the density of y given x and omega? And why we estimate it? How do you estimate it? Yes, this is the neural network. Okay, the neural network is modeling this thing. Okay, so the output of the neural network will be, or when we join them all together over the data set, will be this term, the likelihood. Okay, that's exactly what we did when we did maximum likelihood estimation. We started from this expression that we've rewritten as a product of likelihood over the conditional densities over the terms, and then we moved on using simply the architecture or the assumptions of the neural network. Okay, but so this is where we have the neural network, and you see the dependence through the omega parameter. Okay, the omega are the parameters of the neural network. Okay, can we evaluate this? So this is more difficult because this is equal to, so this is the marginal density of the data. Okay, so that means you would need to consider all possible neural networks with their prior probability omega, and then compute the probability of the data or the density of the data given this neural network, and then we need to consider all of those neural networks. Okay, so here we have a gigantic integral, which is like, let's say your neural network is a transformer with hundreds of millions of parameters. So that means you would need to solve this 100 million dimensional integral. There is no way you would be able to do that. Okay, but still this is what we would like to compute, because if we have access to this posterior, then we can use the posterior predictive distribution to model P of y given x. Okay, so the goal is to estimate this thing, the posterior over the parameters given the data. How can we do that? So because of this, it seems difficult to obtain an exact evaluation of the posterior density. Okay? So an alternative is just to be happy with an approximation of that posterior density, but to consider a good enough approximation of that posterior density. Okay? How could we then move on from there? So the goal is to approximate this, the posterior density of the parameters given the data set. Yeah. Mm-hmm. Like you do a Monte Carlo estimation of this integral. So you would so it's like when you do approximate an expectation with an empirical average, you just use realizations, and then you take the average, and the result is an estimate of the actual expectation. So you could do that. You could say, okay, I will have access to realization of the posterior, and then for each of the 10 or so neural networks I can draw from this posterior, I can evaluate the density of the data given X, and then I take the empirical average of these densities. That would be nice, but how do you sample from the posterior in the first place? So if you want to go that way, you need to have a way to sample from this distribution. We'll not see that in this course, but if you really want to have a sampler of these parameters, you could use, for example, MCMC algorithms, which would allow you to sample from this distribution, but also only approximately. Okay, what we'll do instead is to say, okay, I have this target distribution, and I will consider an approximation of that distribution. And I will call this approximation Q. It will be another distribution over the same object, over the parameters. Okay, and this distribution is something which will be flexible and which will come with its own parameters, which I will call nu. Okay, so I have this target distribution, I have this flexible distribution, and what I want to do, or what I could do is to try to align this distribution with this one. Okay? And I could do this in the sense, for example, of the KL divergence between these two distributions, and try to minimize the KL divergence between Q and the posterior. Okay? Do you know about the KL divergence? So it's not a distance, but it's what you call a divergence, which is a function that you can use to measure how similar, in a sense, or how close are two distributions. In this case, it would, so the definition of the KL divergence is the expected value over the first. So this is not something symmetric. This is why it is not a distance of. So if you take the expected value over the Q distribution of the logarithm of the ratio of the two densities, you obtain what we call the KL divergence. Okay? So this is just a definition of the KL. And what we want to do is to minimize this guy with respect to the parameters of the Q distribution. Yes? Yeah. Yeah. That would be nice. That would be really nice. And that's a very good suggestion, except that W, what's the size of W? Is the number of parameters you have in a neural network. So for any modern neural network, you would have in the order of, I don't know, between 10 to the 6 to 10 to the 12 parameters. And you will not be able to fit a normalizing flow on something that large. Okay, so how do we proceed from there? So now that I have this objective, so just maybe to make it clear, you could say, like the simplest choice would be to say that Q is a normal distribution over the parameters. And if it's a normal distribution, that means that nu is made of the mean parameter and the variance that we need to specify this Gaussian. Okay? And then we would be minimizing this divergence by trying to find good values of these parameters. Okay? Okay, so this is what we'll call variational inference. This. And if we move on, so this KL can be rewritten like this. I mean, that's the definition of the KL. And we can rewrite it further. Okay, so we can rewrite the log of the ratio of as the difference of the two logs, of the numerator and the denominator. Minus log of this, okay? And this is the posterior, which I can itself rewrite in this way. Okay? Minus log of this quantity, which I can explode. I will do that in the next step. Right. Alors. Okay. So, with respect to the minimization objective, I can remove everything which does not depend on Q. Okay, so this remains. This remains because I'm sampling the parameters from Q. This remains too, but this one does not depend on Q or anything that Q generates. Okay, so this one I can remove. Okay, and now so I will rewrite the minimization now of this quantity as a maximization over the parameters of Q. And I will have Q. So I'm maximizing the negative of this expression. So I will have this first. Log of P of T. And then I will have the negative of log Q minus log P, which is the same as log P minus log Q. Okay. And that further simplifies to minus KL of Q nu and the prior. Okay, so what does that mean? It means that we can rewrite the minimization of the KL of some approximate distribution with the target posterior as the maximization of this quantity, which says you should pick the Q distribution such that you will maximize this thing, which is you will only pick W configurations that do explain the data well. But at the same time, since we are maximizing, you should, because of the negative penalty, you should consider a distribution of our parameters which remain close in the sense of the KL to the prior. Okay. And this thing is what we call the elbow for evidence lower bound. And this is the equation we'll use to derive next time variational autoencoders and next time the diffusion models. Okay, so that gives us basically an objective to maximize, to find an approximation Q, which will remain close to the prior, but at the same time will explain the data. And if we can obtain this thing, a good enough distribution Q, if we say, for example, that Q is a Gaussian, okay, but what will happen now is that instead of trying to sample with a complicated algorithm like MCMC from this distribution, we'll be sampling from our approximation. Okay, and then we'll have an approximation of the posterior predictive distribution. Okay, so this is what you have in the slides, where I've just shown that minimizing the KL between Q and P is the same as maximizing the elbow. Okay, and now that we have this objective, what we can do is to further approximate this expectation with one random realization of the parameters that we draw randomly from Q. Okay, and so to obtain an algorithm which would say at every iteration you sample some parameters omega hat from the current parameterization of Q. Then we do one step of maximization with respect to nu. Okay, so we just evaluate the inside now of this expectation at the value of the parameters omega hat that we have computed. So we have the log of d of omega, that's this term, minus the logarithm of the ratio of the densities, okay, where we further approximate also the KL by this single realization omega hat. Okay? So that gives us a proxy, an objective that we can try to maximize, and we'll do that using gradient ascent in this case, so we can differentiate now this expression. Everything is differentiable. We can compute a gradient and do a step on the new parameters, and then we can iterate. Okay? And so in the context of Bayesian deep learning, this procedure is something we call Bayes by backprop, where we just do gradient ascent on random realizations of the Q distribution. And that's something you can just follow, and then you will obtain an approximation which you can use after as an approximation of the posterior to compute this posterior predictive distribution. Okay? Does that make sense to everyone? Okay. But there is something simpler than all of this, which is dropout. So dropout is something very silly, which I will describe first in a way which seems completely unrelated to anything I've been talking about so far. So dropout works as follows. You take a regular neural network, And then in between two layers, so for example, in between a linear layer or in between two hidden layers inside an MLP, you insert these dropout layers, and the effect will be to mask out randomly some of the outputs. Okay, so the neural network will do as if some of the nodes were disappearing at random. Okay, so for example, here you would say that, you would call the dropout layer, and randomly it would remove, for example, this node, this node, this node, and this node. Okay, and you do really as if these nodes were not part at all of the neural network, but you compute a regular prediction, but without using these nodes to obtain some output, and then you backprop as usual to obtain a gradient, and then do a step. Okay? And the goal of this procedure was initially to avoid overfitting. Okay? So the goal was to have a neural network which would be more robust to random changes in the inputs by forcing the information to be spread inside the network. You would have different paths inside the neural network processing the same information, which is necessarily something which is forced to happen if you say that randomly some of the nodes will disappear. Okay? And that was like the hand-wavy motivation that was provided with this algorithm. Okay, we just forced robustness through this argument, which is not very formal. And then what do we do then at test time when really we want to make predictions? So this is something that happened at training time, but at test time, of course, you want to use all the nodes, all the neurons inside the neural network. And so the trick is just to say, well, you could either make predictions using the entire neural network without removing nodes randomly, but you would just then be rescaling the weights by the dropout probability. So if you say that a node can disappear with a 20% probability, then if you say that at test time they all remain, then you should just rescale down by 1 minus that probability to have some output. So this is what was done initially, but this is not very principled either. The correct procedure should be that you just assume that dropout remains at test time, but every time you will do a forward pass, you will just produce a random realization of the neural network. Okay, so basically we will sample T neural network using dropout. Each of them will correspond to a randomly perturbed neural network like this. You compute their predictions, and then you take the average. Okay? So all of this seems very silly, but empirically that works very well. So these are, this is the classification error for some neural network without and with dropout. And you see that indeed that improves the accuracy. This is something also we did when we implemented the transformer architecture. If you remember, at some point I added a few dropout layers at a few places, and there was an improvement that we could see already on the small data set that we consider. Okay, why does it work? Why does dropout work? So, in a sense, intuitively, it makes the learn weights of a node less sensitive to the weights of the other nodes. Okay? Which force the neural network to learn several independent representations of the same patterns, which therefore will decrease overfitting. So this is the hand-wavy explanations you can find in the original paper, but later on it was discovered that actually dropout is doing Bayesian deep learning. So actually dropout works because fundamentally when you follow this procedure of sampling T neural networks with dropout and then averaging their predictions, you are doing Bayesian model averaging, meaning you are approximating this quantity. Okay? Why is that? So what I'm claiming is that dropout does variational inference. If you just insert these dropout layers, do the regular stochastic gradient descent training, you would be effectively doing you would be effectively maximizing the elbow. Okay, if that's true, that means dropout corresponds to some choice of the Q distribution. Okay, which we call the variational family, in this case, over the parameters. And in this case, we can see this is true by making this choice for Q. So if we split so if omega corresponds to the union of all the parameters, if we split them by layers, and we just consider for the sake of simplicity here linear layers, so we have this bunch of matrices, these W matrices, and we can further split the matrices by the units, the neurons that are connected from one layer to the next. Okay. So that's the ways that we would have in a regular MLP. Then we can define the variational parameters nu, okay, the ones we will be effectively maximizing when we do that. So this parameter nu as matrices that correspond similarly to layers and inside the matrix to nodes. Okay. And then we can say that given these notations, Q over network parameters given M, okay, is defined simply as the joint distribution, so the product of the densities of the weight matrices, the W, conditionally on the parameters M for that part of the variational family. And then each of these terms is itself decomposed as a product of marginal densities over the weights connecting a node, okay, given the corresponding parameters in the variational family. And then, and that's where dropout should reappear, we are saying that Q of W given M is defined as a mixture of two delta distribution, as a mixture of two Dirac distribution. It's either a Dirac distribution. So if we say that the density of some vector W of parameters given M, we say that the density should be centered at 0 with some probability P, which is the probability of just removing the node, the dropout probability, or we keep the node, and in this case that happens with a probability of 1 minus P, and we center, in this case, the density at M. Okay? Does that make sense to everyone? Or to someone? Okay, so if we make this choice for Q, and then we follow this, what you will see is that we recover stochastic gradient descent on the regular objective function. Okay, so we make this choice for Q, which is the same as dropout. Okay, so effectively what would happen is that if we want now to sample parameters, if we want to sample omega hat that we need when we do this step 1, we need to sample from Q. Okay. So we would do that by just drawing these binary variables from this bunch of Bernoulli distribution of parameters 1 minus P for each layer I and each unit K inside these layers. Okay. Then we just select what remains. We select the parameters that will remain after we remove these nodes, and we can write this in this way. So W hat will correspond to M times this diagonal matrix, which is just made of ones and zeros, but basically just selecting the columns of M's we should put inside W. Okay. And so it's as if we take a regular linear layer, we take some columns at random, and we set them all to zeros. Okay, so it's the same, strictly equivalent as just saying we remove the node entirely. Okay, meaning this Q distribution is equivalent to dropout. Do you agree with that? Okay, then if we go further, so now we know to sample from Q, and we have said it's equivalent to randomly setting units of the network to 0, which is the same really as doing dropout. And then step 2 of base by backprop, we do a step of gradient ascent on this estimate of the elbow. And so we would maximize the logarithm of the density of the data given these parameters W hat minus the KL between Q and the prior. Okay, and we do a maximization step. But usually what we do in deep learning is we minimize the negative of the log density. Okay, but that's equivalent if we say, okay, I take the negative of this previous objective, L hat, and now I would be minimizing, I would have this term instead. I would be minimizing minus log of the density of the data given parameters W hat plus this KL term. Okay? And already there, you should see that this is the first term, at least, is the regular objective. Okay? It's when we do maximum likelihood estimation, we minimize the negative of the log density of the data. Okay, except that now you do that at random parameters W hat, which you obtain because you are removing randomly because of the dropout layers that you've inserted in the architecture. Okay? And then we still have this term, however, which is not something we have seen before. We have the KL term, the KL penalty, between Q, the Q distribution, and the prior that we have about parameters. And usually in what you've seen so far, we were not considering this term. But that's something maybe you have seen in other contexts, in machine learning maybe, where you could have fit a linear model plus, for example, some penalty on the coefficients of the linear model. Okay? And if you say, for example, that this penalty is the L2 norm over the coefficients, actually that's the same as saying you have, in this case, a Gaussian prior over the parameters. And in this case, the KL between Q and these Gaussian priors will be really analytically the same as having an L2 penalty on the coefficients, or in this case, on the weights. Okay? So this is what I'm saying also there. If your prior is Gaussian, minimizing this KL is equivalent to having an L2 regularization on the weights. But you could have, of course, other beliefs. You could say that you have a Laplacian beliefs on the weights. And in this case, minimizing the KL would be equivalent to having an L1 penalty term. Okay, so another way to say the same thing is that what I've just shown you is that if you take the regular deep learning recipe and you just insert dropout layers, it's the same as being Bayesian now and doing variational inference implicitly over the weights of your neural network. Okay? So basically, you can just forget everything I've said, and if you want to estimate epistemic uncertainty, you can just add a few dropout layers here and there, and you will be capturing some of this variability due to the fact that there might be many good neural networks fitting the data. Okay? Okay, so now that we have these mechanisms, we can extract out uncertainty estimates. So this is just for your information, but this is very obvious. So the way you do that, if you want to compute, let's say, the expected value of the posterior mean, you would just be sampling randomly neural networks, T of them, and then you average their predictions, and you can similarly also derive a good expression for the variance based on this mechanism. Okay, and this is a demo. Maybe I can switch to some. No. Is this one? Yes. So this is fitting the data using this variational inference procedure based by backprop. And if we show the uncertainty, you see that this part and this part, you have larger uncertainty than where there is data. Okay, but this is exactly what I was trying to explain there. Where you have no data, basically you fall back to your prior in this case, and so you would be as wide as your prior. And where you have data, you reduce the uncertainty by quite a lot. And I can add a few points if you want. Oops. So in this case, this one is doing both the estimation of the, I think, if I'm not mistaken, of the aleatoric uncertainty and the epistemic uncertainty. Of course, you can mix the two of them together if you want. Okay, and why is this useful? This is the last example, an application from computer vision, where the task is to do depth estimation. So from an image, you want to tell if the pixel is close or very far away from the observer. So this is a task which is very easy to do for us, at least within some range of value. But for example, you would like to say that you would like to train a neural network, which would say that these pixels, they are close, they are not deep into the image. On the other hand, pixels there that correspond to the sky, they are very, very far away. And so the task is a regression task over the pixels. But of course, you might be uncertain about the predictions for several reasons. So for example, so the second column, if I'm not mistaken. So the second column corresponds to the ground truth, for which you have noise because of the instrument. You have limited range. So you see all the black pixels correspond to pixels that are too far away, from which the sensor cannot make any reliable measurement. This is the posterior mean produced by the neural network. And so you see that everything in blue is close, everything in red is further away. But if at the same time you can decompose the uncertainty, for example, and specifically into aleatoric and epistemic uncertainty, you would have, if I'm not mistaken, aleatoric uncertainty here for the fourth column and the epistemic uncertainty there for the fifth column. Okay, and you see there that aleatoric uncertainty is high in regions where there are quick changes in the depth. And so, for example, in between the leaves or the branches of this tree, the tree is close, but just a few pixels next to it, you go directly into the sky. And so there is a quick change of value. And of course, these quick changes of value, that's something that you cannot perceive really well because of your instrument. Okay, so that's the noise. These regions will be noisy, and this is where you see also that the neural network is quite uncertain about these edges. Okay? Questions? No? If not, that's it for today. Thank you. So there is no classes for 2 weeks, and then we resume. When is it? In May, I think. Yes, on the 9th of May. Okay?